Hey guys, and welcome back, and today we're talking about linear and nonlinear functions. So today's learning target is going to be to determine if a relation is a function. Remember, a relation is any set of ordered pairs, any set of coordinates. So we're going to determine if those relations are functions, and specifically focusing on our success criteria of justifying if a function is linear or nonlinear. That means we're going to need to talk about what it means to be linear or nonlinear. So let's look at the key idea here. We have a linear function is a function that has a constant rate of change. What that means is it is unchanging. Okay, so I'm going to write that right below the word constant, unchanging. Okay, because we've seen in the past that we can calculate rate of change from different points on the graph. So if you notice that the rate of change is staying the same or is unchanging, we know it's linear. We have in an earlier lesson you learned that the slope of a line is a ratio that compares a vertical change to its corresponding horizontal change. So remember our slope formula. Remember that's also rise over run. That's also the formula when you're given two coordinates, y2 minus y1 over x2 minus x1. Okay, so we're going to consider the following set of ordered pairs in order to illustrate what I mean by a linear function. In fact, our definition for linear function would probably be easier remembered if we just remember that something that is linear forms a straight line. So let's plot these 4 points down and see if it forms a straight line, and we'll also calculate some rates of change. So we have 2, 1, that's that point there, 5, 3, 8, 5, and 11, 7. Okay, so there's our 3 points, or 4 points, excuse me, and I'm going to connect them with a line. Seems like they're pretty straight, okay, but I'm also going to double check and make sure this is indeed a perfectly straight line by checking its rise and run along the way. So if we look from point to point, I see a rise of 2 and a run of 3. Okay, so rise 2, run 3. Okay, and I can see that from the next point. Rise 2, run 3. Rise 2, run 3. So it seems like the slope is unchanging throughout the entire graph. So that's what we're going to be looking for. Let's make a note. Linear functions, okay, linear also means straight line. The root word in linear is line. So we should think of a straight line when we say the word linear. The other idea here is if it's nonlinear. Okay, now that should be pretty straightforward. If we understand the word linear, we should understand the word nonlinear. Not just crossing it out, I wanted to highlight that. Okay, nonlinear. Okay, meaning that it's not a straight line. And I'm going to write that down as well. Not a straight line. Okay, but by textbook definition, nonlinear functions are functions that do not have a constant rate of change. The graph of a nonlinear function is not a straight line. So when we calculate these rates of change, let's do that in the table just to illustrate that this is not linear. I can tell in the input column we go up by ones. So to go from 0 to 1, you have to add 1. To go from 1 to 2, you have to add 1. And to go from 2 to 3, you have to add 1. Okay, so I'm seeing just to add 1 on all the inputs. But then on the outputs, from 3 to 5, that adds 2. From 5 to 6, that adds 1. From 6 to 5, that subtracts 1. And then from 5 to 3, that subtracts 2. So as you can see, the rates of change, if we go input to output, or output to input, I should go, because our slope Slope is rise over run. And remember, rise is y's. So I'm going to take 2 and put it over 1. That's going to be the slope from 0, 3 to 1, 5. If I compare that now to the next one, I get 1 over 1. And the next one, I get negative 1 over 1. And the last one, I get negative 2 over 1. Now, all of these numbers are not equal to each other. If we had a linear table, even if the numbers were changing on the y value, you would see that they would reduce down to the same thing. And we can even see by plotting these on the graph that it does not form a straight line. So I've got 0, 3, 1, 5, 2, 6, 3, 5, and 4, 3. Okay, so there's that function. It is a function because it does pass the vertical line test. And for every input, there's only one output. Okay, it's just not a straight line. In fact, if we look at the context of this graph, it says height of a juggling ball. So it kind of looks like the path that a ball would take if you're throwing it from one hand to the other. Okay, so this one is a nonlinear function. All right, so let's go ahead and try the first example. It says graph each set of ordered pairs to determine if it represents a linear function. If it does, find the rate of change. So let's start with A here. We're going to plot these points down. And really we're just looking out for if it forms a straight line. Okay, so I'm going to make my point a little bigger here. And a little smaller. There we go. Okay, so we've got 1, 5, and 2, 7. So we're trying to figure out how to see everything. There we go. 1, 5, right there. 2, 7. 3, 9. 4, 11. And 5, 13. So that's looking pretty straight to me. I'm also going to connect them. If the directions don't say you have to connect the dots, it's not going to be a requirement, but you should be forming a line and putting an arrowhead on both sides. Okay, now since this is a straight line, this is going to be linear. You can also place your points in a table and calculate the rate of change. So we have our inputs being 1, 2, 3, 4, and 5. And our outputs, we have our 5, 7, 9, 11, and 13. And if we calculate that rate of change, I see on the input side they are increasing by 1. And on the output side, 5 to 7 is adding 2, 7 to 9 is adding 2, 9 to 11 adding 2, and so on. So I'm seeing my rate of change is always going to be output 2 over input 1, or just 2. So since the rate of change is constant, that's just another way we've proved that this is, in fact, linear. So you can either say the graph is showing a straight line, or you can say the rate of change is constant. So let's take a look at this other one here. We need to plot the points 0, 0, 1, 1, 2, 4, and 3, 9. Okay, so that one looks like it is curving a little bit. Okay, so we can kind of see this U shape going on. Okay, so since it is not straight, the points are not lined up perfectly, we would say that this is nonlinear. And if we take a look at the table, and no, you don't have to make a table every single time, just make sure you're following directions. If we make a table, I can prove more so that this is not linear. So I'm going to take all my inputs first. 0, 0, 1, 2, 2, 3. And then all my outputs. 0, 1, 4, and 9. That would say 5. I want 9. Okay. And now just take a look at what the rate of change looks like. So all the x's I'm seeing are increasing by 1. But on the y side, I see from 0 to 1 is adding 1. From 1 to 4 is adding 3. And from 4 to 9 is adding 5. So if we make those rise over run ratios, we have 1 over 1, 3 over 1, and 5 over 1. Well, 1 is not equal to 3, is not equal to 5. So since even the table now is telling us that the rate of change is not constant, I really further have proved that part B is non-linear. So in this first example, we had a linear graph and a nonlinear one. Let's have you guys try this on your U-Try. Go ahead and plot the points, see what they look like on the graph, and determine whether it is linear or nonlinear. Alright, now I know you guys just tried one of these, but I want you guys to try another one, and this one's just identification. So label each graph as either linear or nonlinear. Alright, so let's take a look at a second example. It says determine whether the tables represent a linear or nonlinear function and explain. So we're going to use the same type of logic that I used in the key concept slide, where we just look at the changes in the inputs and the changes in the outputs. So let's take a look at the first one. I'm seeing that the inputs are increasing by 1 each time. But then the outputs, I'm seeing from 2 to 4, they increase by 2. From 4 to 7, they increase by 3. From 7 to 8, they increase by 1. And from 8 to 10, that's an increase of 2. So if I make my rise over run ratios, or my change in the output over the change in the inputs, I'm seeing 4 different ratios. 2 over 1, 3 over 1, 1 over 1, and then another 2 over 1. Okay, since only 2 of them are equal to each other, that is not linear. All 4 of them need to be equal to each other. So since 2 does not equal 3, does not equal 1, we would say that this is non-linear. Okay, so now let's take a look at the second one. The inputs are increasing by 3. Whereas the outputs, I'm seeing from 0 to 1 is 1. From 1 to 3 is 2. From 3 to 6 is 3. And from 6 to 10 is 4. Now, this is a pretty neat pattern. Okay, it goes 1, 2, 3, 4. But that's still not linear, because if we look at those ratios of outputs over inputs, we have 1 over 3, 2 over 3, 3 over 3, and 4 over 3. If you were to type these 4 ratios in your calculator, they would not equal each other. If I gave you 1/3 of a pizza and someone else 2/3 of a pizza and someone else 3/3, which is the whole pizza, okay, you wouldn't think that's very fair, nor would you think 4/3, which is a whole pizza and another slice. Okay, so those are not equivalent. This is, again, nonlinear. I apologize for my messy handwriting there. That says nonlinear. That's an N. Okay, and then let's look at our last one. Okay, so I see in the inputs increase of 1 all the way down. And then on the output side, if you're struggling with negative numbers, please double check and think of a number line. Okay, in a number line, if we start at -8 and we go back to -16, okay, which is way over here, you have to go back 1, 2, 3, 4, 5, 6, 7, 8. So you have to travel backwards 8 units. That's -8. So I'm subtracting 8 to go from -8 to -16, not adding 8. Okay, and it's going to be the same thing from -16 to -24. I'm going to have to subtract 8. Subtract 8. Subtract 8. Okay, now that I'm seeing output 8 over 1, 8 over 1. Now I don't need to write these ratios each time, okay, but the reason I am is there may be times where these numbers look like they're changing and it might seem like they're not constant, but if you make the ratios, they'll reduce down to the same thing. But if you ever see them just repeating like this, then you can go ahead and say, all right, they're all equivalent. That would make this linear. Let's have you try this on your U-Try. All right, so let's take a look at a third example, which is more like a real life situation. It says when a scuba diver goes underwater, the weight of the water puts pressure on the diver. The table shows how the water pressure on the diver increases as the diver's depth increases. So the first part here, it says, what is the rate of change of the linear function? Okay, so first thing we're looking for is the rate of change. And what does the rate of change represent in the situation? That's really important. We want to answer both of those questions. We're going to answer what it represents by looking at the titles of what's in the table. Okay, so first let's actually calculate what the rate of change is. In the inputs, I'm seeing add 10 each time. And now, since we're dealing with decimals on the output side, I would recommend first typing in the number that's ahead. So type in 8.8 first in your calculator, and then subtract 4.4. That gives you the difference, which here is 4.4. But now the next one's not going to be that easy. Let's do 13.2 minus 8.8. Again, I'm seeing 4.4. Okay, and again, I'm going to do 17.6, and I'm going to subtract 13.2, which gets me, again, 4.4. So already I can kind of assume that this is a linear model because the rate of change is always going to be that 4.4 over 10. Let's actually write that out. Some of you guys on your last test were mixing decimals and fractions. This is actually a no-no. Okay, to keep it like that, we need to make sure we get rid of this decimal. The easiest way to do that is to multiply by a factor of 10, okay, because this decimal is going to scoot over if we were to multiply it, or divide it, I should say, by 10. When we're dealing with decimals, okay, let's say I'm going to give an example of 3.2. If you want the decimal place to move to the right, that means you are multiplying it by 10. So in order to undo that, you have to do that by dividing by 10. Okay, so if we want to move that decimal place over, we're really multiplying by 10. So this is 44 over 100. Okay, that's the same. If you were to type in 4.4 in your calculator and divide it by 10, and then type in 44 divided by 10 or 100, you would get the same answer. And now we can actually reduce this fraction down without it being a mixture of decimals and fractions. So I'm going to divide by 4 because I know 44 is divisible by 4 and I know 100 is divisible by 4, which would give me 11 over 25. So my rate of change here is going to be 11 over 25, which we still need to say what it represents in the situation. So remember, the outputs were the water pressure. So that's 11 pounds per square inch every 25 feet of depth. Okay, so that's important that we put those units on there. So not only are we saying the rate of change, but we're saying what it represents. And I'm actually going to move this over here just to clean this up. You don't have to erase anything, just write this a little lower. I just ran out of space. So this was our rate of change, 11 over 25. And then the meaning, I'm going to write out in a sentence. Okay, so for every 11 pounds per inch squared, the diver will have, let's see, how do we want to phrase this? Swam down 25 feet. Okay, so there's our meaning. Part B says, use the rate of change to predict the water pressure on a diver at a depth of 60 feet and a depth of 100 feet. So what I want to do here is take my rate of change, the equation that we've learned in order to figure out things like this is y equals mx, where rate of change just gets substituted in for the m. So our equation is y equals 11/25 x. Okay, well, here are all the x's. They're saying 60 feet and 100 feet. Well, those are x values. Those are inputs. So I'm just going to substitute those two numbers in for x. So the first one is going to be y equals 11 over 25 times 60. So I'm going to type that in my calculator and see what the output would be. I'm going to do that by just doing 11 divided by 25 times 60. My calculator is giving me 26.4. I can also do that for 100. Y equals 11 over 25 times 100. And again, typing 11 divided by 25 times 100, which gives me 44. So for part B, I can say that my estimation for 60 feet deep would be 26.4 pounds per inches squared. And for 100 feet deep, it would be 44 pounds per square inch. So those are my answers for part B right there. Let's have you guys take a look at your own real life example. Give it a shot. Alright guys, so I've got one more example for you. It says, suppose there are 20 rabbits on an island and the rabbit population can triple every 6 months. I'm going to highlight some of that information just because we're going to have to use it. In part A, it says, make a table of values to find how many rabbits there would be after 2 years. We should also make a note here, 2 years, it's asking for every 6 months. Those are two different units. So I'm going to say 2 years is 24 months. So that when I make my table, I'm really looking for 24 months. Okay, so I have time will be on the input. Okay, so the months. And then the number of rabbits is going to be the output. Okay, so let's, since it's tripling every 6 months, let's go by intervals of 6. So let's say no time passes, 6 months pass, 12 months pass, 18 months pass, and 24 months pass. And right at the 24-month mark, that's when we're going to be able to answer part A. So it says, suppose there are 20 rabbits on an island. Well, that's going to be what we start with. Okay, so as no time goes by, we should be starting with 20 rabbits. Okay, and then now 6 months goes by, and that number is going to triple. Okay, well, 20 times 3 would be 60. Now, it says it triples every 6 months, so if another 6 months go by, I need to then multiply the 60 by 3 as well. So 60 times 3 is going to be 180. I need to, again, triple 180 because I have another 6 months that goes by. That's 540. And then I need to triple that again, which is 1620. Okay, so for part A, I can say there are 1,620 rabbits after 2 years. Part B says, does the relationship represent a nonlinear function? Okay, so it's asking, is this nonlinear? Let's look at the rate of change that we've created from this table. So I made it so that we're adding 6 every time. So I know on the input side, it's all adding 6. But then on the output side, from 20 to 60, we add 40. From 60 to 180, we add 120. From 180 to 540, let's see, I don't know, I need to grab my calculator. 540 minus 180 gives me 360. And then my difference between 1620 and 540, that's 1080. Okay, so I can clearly see that these numbers are not the same. Remember, output over input for your rate of change, 40 over 6 does not equal 120 over 6, does not equal 360 over 6, does not equal 1080 over 6. If you were to type these 4 ratios in your calculator, you would not get the same decimal. So since they are not equal to each other, we can say yes, okay, because the rate of change is not constant. Okay, so we're saying yes to it being nonlinear. Okay, yes, because the rate of change is not constant. It's not the same each time. Last part of this question says, using the table, when would you expect the rabbit population to reach 1,000, or not 1,000, woof, that is 1 million rabbits. Oh boy. Okay, so what I would do is continue this table. Okay, so I'm just going to make a new column down here since I kind of wrote underneath my last table. Okay, I've got my X and my Y. Remember, my X is my time. Okay, my Y is my population of rabbits. Okay, so I'm going to start at 30 months because that would be 6 months after that 24-month mark. Okay, and I'm just going to go down the line. Let's do 30, 36, 42, 48. We'll see where we get with 48. And again, we need to triple it every time. So we need to take that 1,620 and triple that. My numbers are going to get really large here, so I'm going to write kind of diagonally. Okay, so right now I'm just taking each number, multiplying it by 3. Oh, no, I'm still not even close here. Okay, so right now I'm at about, 131,000. I can keep going till I get to about 1 million rabbits. So I got to add 6 more, that's 54 months. Add 6 to that, that's 60 months. 66, we'll see how we get from there. Okay, so my number is getting pretty large so far. I have 393,000 on this one. Here we go. So at the 60-month mark, I'm seeing 1,180,980. So we don't even need to go that far. Okay, so right here, that's where we can answer part C, that in about 60 months, we'll be able to see the rabbit population be about 1 million, which if you want to express that in years, if you divide that by 12, you get 5 years. Okay, let's see how you analyze the next one on your U-Try.
I wouldn't